PSPICE is a circuit simulator valuable for analyzing and designing electronic circuits. Its use spans across electronic circuit designers, and a student version is often freely accessible. PSPICE proves useful in simulating various circuits, including delta transformers. In this specific scenario, PSPICE demonstrates the 1/3, 2/3 rule for a delta transformer when there's a single load on one of the phases. This rule dictates that the voltage observed across the loaded phase equates to 2/3 of the voltage across the phases without a load. The simulation affirms the validity of this rule. An attempt was made to use PSPICE to validate the concept of a 1-to-1 split in an ideal transformer. However, directly connecting the three voltage sources in a delta configuration with zero impedance was not permitted by PSPICE. This limitation arises because PSPICE cannot accurately determine the voltage split within an ideal transformer that has zero impedance. To effectively simulate an ideal transformer exhibiting a 1-to-1 split, the incorporation of resistors in series with each secondary winding is necessary. Introducing these resistors establishes a non-zero impedance, enabling PSPICE to compute the voltage split. PSPICE serves as a tool for electronic circuit designers. It facilitates the simulation of diverse circuits and aids in validating new circuit designs. Delving deeper into PSPICE and its application to delta transformers, it's important to understand the underlying principles and how PSPICE handles different circuit conditions. A delta transformer is a type of three-phase transformer where the primary and secondary windings are connected in a delta configuration. This configuration provides certain advantages, such as the ability to suppress third harmonic currents and maintain voltage stability under unbalanced load conditions. When analyzing delta transformers, several key parameters need to be considered. These include the voltage and current ratings of the windings, the impedance of the transformer, and the load conditions. PSPICE allows you to define these parameters and simulate the behavior of the transformer under different operating conditions. The 1/3, 2/3 rule is a specific characteristic of delta transformers with a single load. When one phase of the delta winding is loaded, the voltage across that phase drops to 2/3 of the voltage across the other two unloaded phases. This is due to the current distribution within the delta winding. PSPICE can accurately simulate this behavior and provide valuable insights into the performance of the transformer under these conditions. Simulating ideal transformers in PSPICE can be challenging because ideal transformers have zero impedance. This can lead to convergence problems and inaccurate simulation results. To overcome this limitation, it is common practice to add small series resistors to the windings of the transformer. These resistors introduce a small amount of impedance, which helps to stabilize the simulation and improve the accuracy of the results. The value of these resistors should be chosen carefully to minimize their impact on the overall performance of the circuit. When simulating delta transformers with PSPICE, it is important to pay attention to the grounding configuration. The grounding configuration can significantly affect the simulation results. In some cases, it may be necessary to add a ground connection to the neutral point of the delta winding to ensure accurate results. PSPICE provides a variety of analysis options that can be used to study the behavior of delta transformers. These include transient analysis, AC analysis, and DC analysis. Transient analysis can be used to simulate the response of the transformer to sudden changes in load or voltage. AC analysis can be used to determine the frequency response of the transformer. And DC analysis can be used to determine the operating point of the transformer under different load conditions. In addition to simulating the electrical behavior of delta transformers, PSPICE can also be used to simulate the thermal behavior. This can be useful for determining the temperature rise of the transformer under different load conditions. PSPICE allows you to define the thermal properties of the transformer and simulate the heat flow within the transformer. This can help to identify potential hotspots and ensure that the transformer is operating within its safe operating limits. PSPICE is a powerful tool that can be used to analyze and design delta transformers. It provides a wide range of features and analysis options that can help you to understand the behavior of these complex circuits. By using PSPICE, you can optimize the design of delta transformers and ensure that they meet the required performance specifications. When working with PSPICE, it's crucial to establish a clear understanding of the transformer specifications. This encompasses voltage ratings, current capacities, impedance values, and the intended load profile. Accurate input of these parameters into PSPICE is paramount for achieving reliable and meaningful simulation results. Furthermore, the choice of simulation type plays a crucial role. Transient analysis is suitable for examining the transformer's response to sudden load variations or voltage fluctuations, offering insights into its dynamic behavior. AC analysis, on the other hand, helps determine the transformer's frequency response, revealing how it behaves across different frequencies. DC analysis is useful for establishing the transformer's operating point under specific load conditions, providing a snapshot of its steady-state performance. Addressing the challenges of simulating ideal transformers with zero impedance requires a practical approach. Inserting small series resistors into the windings introduces a slight impedance, which stabilizes the simulation process and enhances the accuracy of the results. However, it is crucial to carefully select the resistance values to minimize any impact on the circuit's overall performance. Too high a resistance can distort the results, while too low a resistance may not adequately address the convergence issues. Grounding configurations also warrant careful consideration during PSPICE simulations. The grounding scheme can significantly influence the simulation outcomes. In certain scenarios, grounding the neutral point of the delta winding becomes essential to ensure accurate results. PSPICE versatility extends beyond electrical simulations, allowing for the analysis of thermal behavior within delta transformers. This feature is particularly valuable for assessing temperature rise under diverse load conditions. By defining the thermal properties of the transformer and simulating heat flow, PSPICE helps identify potential hotspots and ensures operation within safe limits. This capability is crucial for preventing overheating and potential failures. In summary, PSPICE serves as a potent tool for thoroughly analyzing and designing delta transformers. Its extensive features and analysis options provide valuable insights into the intricate behavior of these circuits. By leveraging PSPICE, engineers can optimize transformer designs, ensuring adherence to performance specifications and enhancing overall system reliability. Furthermore, understanding the limitations of PSPICE and employing appropriate techniques, such as series resistors for ideal transformers, is crucial for obtaining accurate and reliable simulation results. The application of PSPICE extends beyond basic circuit analysis, enabling the investigation of complex phenomena such as harmonics and inrush currents. Harmonics, which are integer multiples of the fundamental frequency, can cause various problems in power systems, including increased losses, equipment overheating, and interference with communication systems. PSPICE can be used to simulate the generation and propagation of harmonics in delta transformers, allowing engineers to design mitigation strategies. Inrush currents, which are large transient currents that occur when a transformer is energized, can also cause problems such as voltage dips and equipment damage. PSPICE can be used to simulate inrush currents in delta transformers, allowing engineers to design protection schemes to minimize their impact. The accuracy of PSPICE simulations depends on the quality of the models used to represent the transformer components. Transformer models typically include parameters such as inductance, resistance, and capacitance. These parameters can be obtained from manufacturer datasheets or through experimental measurements. It is important to use accurate models to ensure that the simulation results are reliable. PSPICE also allows users to create custom models for transformer components. This can be useful for simulating transformers with non-standard designs or for incorporating nonlinear effects. Creating custom models requires a good understanding of transformer theory and modeling techniques. When using PSPICE to simulate delta transformers, it is important to validate the simulation results against experimental data or other simulation tools. This helps to ensure that the simulation is accurate and that the results can be trusted. Validation can be done by comparing the simulated voltage and current waveforms with measured waveforms, or by comparing the simulated performance characteristics with those obtained from other simulation tools. PSPICE is a constantly evolving tool, with new features and capabilities being added regularly. It is important to stay up to date with the latest developments and PSPICE to take full advantage of its capabilities. There are many resources available to help users learn about PSPICE, including online tutorials, training courses, and user forums. By investing time in learning about PSPICE, engineers can significantly improve their ability to analyze and design delta transformers. Furthermore, considering the broader context of power systems, delta transformers play a crucial role in voltage transformation and power distribution. They are widely used in industrial facilities, commercial buildings, and residential areas to provide the appropriate voltage levels for different types of equipment. The efficient and reliable operation of delta transformers is essential for ensuring the stability and performance of power systems. PSPICE simulations can help engineers to optimize the design and operation of delta transformers, leading to improved energy efficiency, reduced losses, and enhanced reliability. In addition to its applications in power systems, PSPICE can also be used to simulate delta transformers in other areas, such as electronics and communications. For example, delta transformers are used in some types of radio frequency RF circuits to provide impedance matching and isolation. PSPICE can be used to simulate the performance of these circuits and to optimize their design. The use of PSPICE in simulating delta transformers requires a systematic approach. Firstly, define the problem clearly, outlining the specific aspects of the transformer's behavior that need to be investigated. Secondly, gather accurate data, including transformer specifications, load conditions, and any relevant operating parameters. Thirdly, create a detailed PSPICE model, ensuring that all components are accurately represented and connected. Fourthly, run the simulation, selecting the appropriate analysis type and simulation parameters. Fifthly, analyze the results, carefully examining the waveforms, voltages, currents, and other relevant data. Sixthly, validate the simulation, comparing the results with experimental data or other simulation tools to ensure accuracy. Finally, document the process, recording all assumptions, data, models, and results for future reference and analysis. This systematic approach ensures that PSPICE simulations are conducted effectively and that the results are reliable and meaningful. In addition to the points mentioned earlier, when modeling a delta transformer in PSPICE, it's crucial to accurately represent the core characteristics. The core's magnetic properties, including its permeability and saturation behavior, significantly influence the transformer's performance. PSPICE allows you to define these properties using appropriate models, such as the Giles-Atherton model, which captures the nonlinear behavior of ferromagnetic materials. Accurately modeling the core is essential for simulating phenomena such as core losses and saturation effects, which can impact the transformer's efficiency and voltage regulation. Furthermore, consider the impact of temperature on the transformer's performance. The resistance of the windings and the core losses both vary with temperature. PSPICE allows you to define temperature-dependent parameters, enabling you to simulate the transformer's behavior under different thermal conditions. This is particularly important for applications where the transformer operates in harsh environments or under heavy load conditions. Also, it is important to consider the effects of aging on the transformer's performance. Over time, the insulation in the transformer can degrade, leading to increased losses and reduced reliability. PSPICE can be used to simulate the effects of aging by incorporating appropriate models for insulation degradation. This allows you to assess the remaining life of the transformer and to plan for maintenance or replacement. In the realm of power electronics, delta transformers find extensive use in applications such as rectifier circuits and inverter systems. These applications often involve nonlinear loads and switching waveforms, which can generate harmonics and other undesirable effects. PSPICE can be used to simulate these circuits and to optimize the design of the transformer to minimize these effects. For example, PSPICE can be used to design filters to attenuate harmonics and to optimize the transformer's impedance to improve the power factor. When simulating delta transformers and power electronic circuits, it's important to use appropriate models for the switching devices, such as diodes and transistors. These models should accurately capture the switching characteristics of the devices, including their turn-on and turn-off times and their voltage and current ratings. PSPICE provides a variety of models for switching devices, allowing you to simulate the behavior of these circuits accurately. Furthermore, consider the effects of electromagnetic interference EMI on the transformer's performance. Transformers can generate EMI, which can interfere with other electronic equipment. PSPICE can be used to simulate the EMI generated by transformers and to design mitigation techniques such as shielding and filtering. Modeling EMI accurately requires a good understanding of electromagnetic theory and modeling techniques. In addition to its use in analyzing and designing delta transformers, PSPICE can also be used for educational purposes. PSPICE can be used to create interactive simulations that allow students to explore the behavior of delta transformers under different operating conditions. These simulations can help students to develop a deeper understanding of transformer theory and to learn how to apply this knowledge to real-world problems. PSPICE is a powerful and versatile tool that can be used for a wide range of applications related to delta transformers. By mastering PSPICE, engineers and students can significantly improve their ability to analyze, design, and operate these important components of electrical power systems. The advancements in PSPICE continue to enhance its capabilities for simulating complex electrical systems, including delta transformers. Newer versions of PSPICE often incorporate improved algorithms for solving nonlinear equations, which can lead to faster and more accurate simulations. They may also include enhanced model libraries with more detailed and accurate models for transformer components. Keeping abreast of these advancements is essential for maximizing the benefits of PSPICE simulations. When using PSPICE for advanced simulations, consider using techniques such as subcircuit modeling and hierarchical design. Subcircuit modeling allows you to break down complex circuits into smaller, more manageable blocks. This can simplify the simulation process and improve the accuracy of the results. Hierarchical design allows you to create a modular design where each module represents a specific function or component. This can make it easier to reuse and modify your designs. Also, take advantage of PSPICE scripting capabilities to automate repetitive tasks and to create custom analysis routines. PSPICE supports a variety of scripting languages, such as MATLAB and Python, which can be used to control the simulation process and to post-process the results. Scripting can significantly improve your productivity and allow you to perform more complex analyses. When working with large and complex PSPICE models, it's important to use appropriate techniques for managing and organizing your files. Use a consistent naming convention for your files and folders and create a clear and logical directory structure. Also, use version control software, such as Git, to track changes to your models and to collaborate with other engineers. Effective file management is essential for ensuring that your simulations are reproducible and that you can easily find and modify your models. Furthermore, when presenting the results of your PSPICE simulations, it's important to communicate your findings clearly and effectively. Use graphs and tables to visualize your results and provide clear explanations of the key trends and patterns. Also, be sure to document your assumptions, methods, and limitations so that others can understand and interpret your results correctly. Effective communication is essential for ensuring that your simulations are used to make informed decisions. PSPICE is not just a software tool, it's a gateway to understanding and optimizing the performance of delta transformers in a myriad of applications. By combining a strong understanding of transformer theory with the power of PSPICE, engineers and researchers can push the boundaries of innovation and develop more efficient, reliable, and sustainable electrical power systems.